In this video, I'm going to give a quick demo of the Colab important classification metrics. In the first cell, I install all the required libraries like NumPy, Pandas, and Matplotlib and scikit-learn. And output shows that all the required libraries are ran successfully. Next cell, we generate a synthetic binary classification dataset representing patients who are either healthy or having a specific medical condition. Output shows we created 1,000 patients, roughly 70% being healthy and 30% having the condition. Next, we visualize this metric imbalance with a clear bar chart. The plot instantly shows that there are more than twice as many healthy as patients as there in the patient with the condition. Next, we split our data into training and training set, ensuring we maintain the same ratio of healthy to sick patient. Logs verify that 700 samples went through training and 300 for testing, keeping our class proportion perfectly intact. We train a standard logistic regression model on our training data to act on our baseline classifier. The printed text confirms the model trained successfully and is ready to make predictions on the 300 text samples. Next, we display a sample of the model's prediction alongside the actual labels and its calculated confidence probabilities. The output table lets us peek at individual cases, showing that the model is mostly correct but occasionally makes mistake. Next, we compute the famous confusion matrix using scikit-learn. The output prints a 2 cross 2 number matrix, which forms the foundation of almost classification matrix. Next, we break down the 2 cross 2 grid into our 4 core components: true negatives, false positives, false negative, and true positives. The output clearly maps these out, showing exactly how many predictions were correct versus how many were wrong. Next, we create a color-coded annotated heat map to make the confusion matrix easier to read. The visual output clearly separates the correct prediction in green on the diagonal and error in the red of the diagonal. Next, we classify our single prediction in our test set into the 4 confusion matrix outcomes. The printed summary tallies them up, showing we had mostly true negatives and a handful of false negatives and false positives. Next, we print out specific example of each outcome type to ground them in reality. The text output shows actual cases where the model succeeded or failed, along with its confidence score for those cases. Next, this code visualizes the distribution of prediction probabilities for both healthy and sick patients. The overlapping histograms reveals that the models makes it most errors when its probability is hovering near 50%. Next, we mathematically verify that our 4 confusion matrix value add up to the test size. The output confirms our numbers are solid and predicted and actual totals both predict equaling 300. Next, we calculate the standard accuracy score both manually using scikit-learn. The output shows our model right for about 79.6 of the time, which sounds decent at first glance. Next, sell the test accuracy on a perfectly balanced 50 by 50 dataset to see how it behaves. If you go to the output, shows 80% accuracy, proving that the accuracy is great metric. Next, we demonstrate the accuracy paradox using a highly imbalanced fraud detection dataset where only 1% of transactions are fraudulent. The shocking output shows that a dumb model that always predicts not fraud achieves 99% of accuracy, beating our smart model despite catching zero fraud. Next, we visualize the paradox with pie chart and bar graph. The chart clearly illustrates why accuracy is a terrible metric for highly imbalanced data, as the dumb model looks artificially perfect. Next, to fix this, we introduce balanced accuracy, which averages the accuracy of each class independently. The output proves its worth. The dumb model drops to a realistic 50% while the smart scores 84. Next, we move on to the precision, which asks out of all the predicted positives, how many were actually positive. The output calculates the 71.2%, meaning where we predicted someone is sick. So next is recall, which asks out of all the actual positives, how many did we successfully find. The output shows recall of 56.5, meaning unfortunate missed 40% of sick patients. Next, we plot precision and recall side by side to visually contrast them. The bar chart makes the difference clear. The precision focuses on the quality of our positive prediction, while recall focuses on catching all the actual positives. We adjust the model decision threshold from 0.1 to zero point 0.9 to see how precision and recall react. The printed table shows the classic trade-off, and precision goes up, recall almost always goes down. We plot this precision recall trade-off in a line graph. The intersection of two curves visually demonstrates line balancing act you must perform while tuning a model. Next, we calculate specificity, which measures our ability to correctly identify the negative class. The output provides a complete picture showing we are great at finding healthy patients and a worse sequence, which is 56.5. Next, we introduce the F1 score, which combines precision and recall into a single metric using their harmonic mean. The output shows F1 score is about 0.63, giving a balanced summary of a model's performance on positive class. Next, we explore the F beta family of scores, calculating F0.5, F2 to prioritize precision or recall, respectively. The printed table shows how F0.5 favors our higher precision, while F2 drags the score down by favoring our lower recall. Next, we plot these three F scores on a bar chart of comparison, and the chart clearly shows how choice of beta weight shifts the final metric depending on our business goals. Next, we calculate the Matthews correlation coefficient, a highly robust metric for imbalanced data. The output is strictly honest. It gives our dumb model a 0 while giving smart 0.63. Next, we introduce Cohen's kappa, which adjusts for the probability of the model guessing correctly by pure chance. If you see the output, it gives kappa 0.49, while the interpretation key classification a moderate agreement. Next, we generate ROC curve plotting the true positive rate against the false positive rate across all threshold. The resulting curve and its AUC score 0.85 and shows that model has strong discriminative power overall. Next, we plot the precision recall curve next to ROC curve. The output shows that nothing that PR curves are often more informative dealing with imbalanced data set. Next, we plot to multi-class classification using the famous IRIS dataset with 3 flower state type. The output prints a multi-class classification report showing strong metric across all 3 flower classes. Next, we compare micro-macro weight average strategies for heading multi-class metric. The output shows slight variations in the score and provides guidelines on what went to each averaging method. Next, we run a massive comparison of all metric on imbalanced data set. The output table clearly highlights the metric exposed, the dumb model, and which one fooled by class imbalance. Next, we bundle everything into a single comprehensive classification report function. Output is a beautiful text dashboard summarizing the confusion matrix, score metric, and class specific performance. Next, we generate a synthetic multi-label dataset simulating movies that can belong to multiple genres at once, like action and comedy. The output shows our movie dataset with sample films having list of multiple genres. And then we calculate Hamming loss, a core multi-label metric that measures the fraction of incorrect individual labels. The output shows 17% Hamming loss, meaning about 83% of our individual genre tags were correctly predicted. Next, we calculate subset accuracy, a brutally strict metric that requires every single label on a sample to predict correct. The output drops to 41%, proving just how hard it's to get every single genre right given a movie. Next, we calculate the Jaccard score, which measures the overlap between predicted and actual labels. The output shows that Jaccard scores around 0.6 to 0.7, offering a more forgiving metric than strict subset accuracy. Next, we evaluate precision, recall, and F1 on our multi-label data using different averaging methods. The output table shows how micro-macro averaging applied to the problem where samples can have multiple tags. Next, we introduce advanced ranking metric like LRAP and coverage error, which evaluates the model's confidence score rather than hard prediction. The output gives LRP score, high LRP score, indicating the model successfully ranks the true labels with higher probabilities than false ones. Next, we compile this into a comprehensive multi-label metric report. The output dashboard nicely summarizes example-based metric like Hamming loss alongside labeled based F1 score. Next, we set up a semi-supervised learning scenario dividing our data into labeled, unlabeled, and test set. The output confirms we have only 10% labeled data to train, 60% remains unlabeled. Next, we implement a self-training loop where the model iteratively predicts label as unlabeled for the unlabeled data and adds the confident ones to the training set. The output log shows the model gradually expanding its training pool over 5 iterations as it finds predictions it trusts. Next, we evaluate how good those automatically generated pseudo labels actually were. The output reveals the pseudo labels were nearly 94% accurate. Self training successfully extracted single from the unlabeled data. Next, we compare our semi supervised model against a model trained on the original 10% labeled data. The results show a slightly boost of performance on the unlabeled data, demonstrating the value of semi supervised techniques. Next, we train different three models logistic, random forest, gradient boosting to analyze their confidence score distributions. The output statistic shows how random forest can be overly confident while logistics is more smoothly distributed. We plot calibration curves to see if model's 80% confidence actually translates to being 80% of the time. The visual plot and expected calibration error score shows the gradient boosting is highly calibrated while the random forest is slightly off. Then we do a deep dive into our changing the probability threshold impact precision, recall F1 and accuracy simultaneously. The output tracked these four metrics side by side as threshold slides from 0.010 up to 0.90. Then we run automated methods to find mathematically optimal threshold based on different business goal. The output prints the best threshold for maximizing F1, maximizing evidence J, or hitting a strict 90% precision target. Next, we group our models prediction into confidence buckets to see how accurate correlations with confidence. The output table proves that when the model is highly confident, it is in fact highly accurate. Next, we visualize the bucket analysis with bar chart showing volume and accuracy per bucket. The chart clearly illustrates that while high confidence predictions are very accurate, they make a smaller volume of total prediction. Next, we simulate a real world prediction routing system where highly confident predictions are auto proved but low confidence ones are sent for human review. Next, the output table estimates the cost and accuracy of the hybrid AI human workflow, proving the business value of confidence score. Next, we wrap up the classification section with a comprehensive confidence analysis dashboard. The output summarizes calibration, optimal threshold, and routing cost into one unified view. Next, finally, we transition into regression, setting up a data set to predict continuous number like house prices. The output confirms our data set is ready with house price ranging from 1 lakh K to nearly 6 lakh K. Sorry, 600 lakh $600 K. We calculate the mean absolute error both from scratching and using sklearn. The output shows how our models is off about 7400 on average, which is an easy metric for humans to understand. Next, we calculate a mean squared error, which heavily penalizes large mistakes. The output yields a massive uninterruptible number in squared dollars, demonstrating why MSE is mostly used for optimizing rather than reporting. Next, we take the square root to get root mean squared error, like bringing the metric back into dollars. The output shows on RMSE of $9,318, which is higher than MAE because it's disproportionately pushing large outliner errors. We compute R squared to measure how much of the variance in house price our model actually explains, and the output shows an excellent score of 0.978, meaning our model explains nearly 98% of the data variance. Next, we calculate adjusted R squared, which penalizes adding useless feature to the model. The output table proves that while regular R squared goes up when adding junk features, adjusted R squared correctly goes down. Next, we explore advanced percentage based regression metric like MAPE and SMAP. The output shows our MAPE is about 2%, meaning our predictions are off 2% on average, regardless of the absolute dollar amount. Next, we finish by generating a comprehensive regression metric dashboard. The final output clearly summarizes the absolute dollar error alongside the percentage error and R squared variance. That's it with this Colab demo. Thank you.